Hello, Chemistry 12. This is Mr. Chan, and today we're going to be talking about the third lesson in reaction kinetics, and we're going to be focusing on potential energy diagrams. Now, what are potential energy diagrams? Is potential energy diagrams represents the changes in the potential energy of the reacting particles forming products when they are colliding. So it is focusing not on the speed of the particles, like what we've had with kinetic energy diagrams, but rather what we're doing is we're focusing on whether or not there's enough energy to break the bonds. Now, recall back in Chemistry 11 that energy is required to break bonds and energy is released when bonds are formed. Now, an example of this would be like if we were to take a look at hockey players. Okay, so here what you have is Elias Pettersson from the Vancouver Canucks. And what you can do is you can see the hockey stick in this particular case is bending. This is what we call a flex, and this is where you get this energy to shoot the puck at a certain speed. And so what happens is what you're doing is you're applying potential energy to the stick, and that potential energy is then transferred to the puck, and then the puck goes towards the net. Now, but what happens is sometimes if there's too much potential energy applied to the stick actually breaks. So that's the idea that we're looking at. Is there enough energy to break, in this case, break the bonds to form your products? Now, so what happens is, if we take a look, what you have is with potential energy diagrams, you will notice that the axis is slightly different than what you have for kinetic energy diagrams. On the y-axis, you have potential energy. On the x-axis is you have the reaction pathway. So you have reactants, you have products. Okay, now, the one thing that you will notice is that there's this new thing called the activated complex. Okay, oopsie, go back here. We have this thing called the activated complex. So if you take a look at your notes, what is the activated complex? What that is a point in which the reactants form a high energy, unstable, or low stability, intermediate or temporary compound before forming either the reactants or products. Now, in this particular case, it is the point where the bonds in the reactants are broken and product bonds are being formed. Okay, now, if you take a look in the Hebden textbook, what you have is I want you to take a look on page number 26. And if you take a look on page number 26, what you will see is you'll see this particular substance here called the activated complex. So what happens is in this activated complex, what you have is the breaking of the hydrogen and bromine bonds, okay, which is right here, and the breaking of one of the oxygen bonds, which is right here. And then what you're doing is almost simultaneously, you are forming a hydrogen and oxygen bond and a hydrogen-oxygen bond. So that is what an activated complex is a high energy intermediate compound where bonds are broken and simultaneously bonds are being formed. Okay, now if we were to take a look at, let's say, regular sports, what would be an activated complex would be like a bat hitting a ball for baseball. So this particular situation, the bat and the ball are forming an activated complex. It's high energy, unstable. And what happens is that that energy is used to transform to see whether or not the ball will, be hit a home run or will be a bloop single. Now, for some of you who love the beautiful sport of European football, this would be an example of an activated complex. What you have is you have the ball hitting the person's face, and whether or not that ball has enough energy, and is hit hard enough to translate into potential energy to break the person's nose or to give the person concussion. So this would be like an activated complex. Now, the activated complex, if we gave the example here, okay, is a high energy intermediate compound. And so what happens is that you could think of it as like an imaginary word. So what happens is it is something like hungry and angry joined together, and you know you use the word hangry. Okay. Now, so how does it look? So in this particular case, what we have is we have two different scenarios. Both of these right now, here you have the reactant. Here you have the reactant as well. So both of these are exactly the same. Notice when they collide, they both form this intermediate compound. Okay? And so what this intermediate compound, this is the activated complex. Okay? Now, so again, this is a high energy, unstable intermediate compound. Okay, and now in this particular scenario, situation one, you notice that you get the exact same reactants back. So in this particular case, what happens is you have the reactants formed, reactants reformed, because low energy. Now, recall what happens is that when particles collide, they have to have sufficient energy and correct geometry. In both situation number one and situation number two, the geometry is the same, but you will notice that the energies are lower. And in this particular case, what you have is you have products formed because enough energy. Now, in both scenarios, what happens is you do have the activated complex formed, but what happens is one, there's not enough energy, and the other, there is. What I want to do right now is just show you a quick simulation of what do I mean by activated complex being able to form the reactants and the products based upon the amount of energy. So I'm just going to share the screen here. Okay. So, so what I have here is I have a potential energy diagram. And what you have is you have uh, low kinetic or low energy particles and high kinetic energy or high speed, high energy particles. Now, as they collide, notice it forms the activated complex, but because there isn't enough energy to break the bonds, what happens is the particles just come together and then they break apart again. Conversely, if you have high energy, what happens is they are able to form the activated complex, break the bonds, and what happens is you get your products. Okay, so that's the difference between high energy and low energy particles, but they both do form the activated complex. That's the one thing I want you to be aware of. Now, if I go back to the screen, now what determines whether or not they have enough energy? This low energy, notice you get the reactants, high energy, you get the products. What you have here is this little scenario of A. So what is A, if I'm going to highlight this here? If we look on to the next page, what A is the activation energy for the forward reaction. Now, when we talk about the forward reaction, it's considered reading this potential energy diagram from left to right. Okay? Now, what is the definition of this activated complex? Is the energy needed to form the activated complex or the energy needed to be overcome to form the product. So the minimum energy required to have the bonds broken to form the products. How do you calculate the activated complex? Can be calculated by taking the difference between the energy of the activated complex and the energy of the reactants. So in this particular scenario, if I were to take a look here, for A, what I want to do is take the height difference between the reactants, which I will underline here, and the activated complex that's in purple. And what you will see here is this activation energy, so I'll just say activation energy. This would be 150 kilojoules, because that is the energy difference between the reactants and the activated complex. Okay, now if we were to take a look, B is the activation energy of the reverse reaction. Okay, so activation energy of the reverse reaction, or EA reverse. Again, when we're talking about reverse reaction, is reading the diagram from right to left, sorry, and is energy needed to form the activated complex to form the reactants. So in this case, if we were to take a look here, if we were to read it from right to left, in this case here, what I have is I have the products, the activation energy for the reverse. So the activation energy for the reverse, I'm just going to make this a little bit smaller. For the reverse, in this case, would be the height difference between the products and the activated complex. This would be 150 kilojoules. Oh, my mistake. The activation energy here is not 150. It should be 50 kilojoules. Sorry, my bad. Okay, so that's the one thing for you to be aware of. Now, in regards to the activated complex, regardless whether you're reading it from reactants to products or products to reactants, what happens is the activated complex is the same compound for both. Both reactants form the activated complex to form products, and products form the activated complex to form reactants. Okay. Now, the last thing I want to talk about here is something called a change in enthalpy, or delta H. So in this case, the change in enthalpy of the reaction of delta H is the energy of products minus the energy of reactants. And if delta H is a positive value, then the reaction is considered endothermic because energy was absorbed in the reaction. Now, you folks were exposed to this back in grade 11. And the one thing about a positive delta H is, if I were to put here, the surroundings get colder. Now, when we talk about surroundings, what that means is basically things that you see or feel. Okay, that would be our surroundings. Now, so if we were to take a look at a reaction, so if we were to do a general reaction, we would have reactants plus energy would give you the products, or the reactants giving you products, and delta H is some sort of positive value. Okay. Now, this you should remember from Chemistry 11. If delta H is a negative value, if we have that here, if delta H is a negative value, then the reaction is exothermic because energy was released into the reaction. And in this case, if energy is released into the reaction, what happens is the surroundings get hotter. Okay. Now, if we were to take a look at the reaction, if we were to write it out, we could write it in two different ways, where we have the reactants going to products plus energy, or you would have the reactants, oopsie, reactants gives you products, and delta H is some sort of negative value. Okay. So if you were to take a look at your notes, notice where the energy term is for the endothermic reaction and the exothermic reaction. And notice what's the difference in terms of the delta H value for an exothermic and an endothermic reaction. Now, again, this should be a review of Chemistry 11. Now, you can take a look at this if in your Hepton textbook, if you take a look on page number 13, they talk about enthalpy changes, all right? And if you take a look on page number 14, they talk about endothermic and exothermic reactions. So on the bottom of page 14, notice here, you notice where the energy term here is for an endothermic and the value of delta H. Now, why do they seem to be opposite? Again, you take a look. For an endothermic reaction, what happens is energy is entering into the chemical reaction. That's what the system is. Surroundings is what we feel. And because energy is going into the surroundings, the system or the reaction is increasing in energy. That's why you have delta H being a positive value. And because the reaction is absorbing energy, energy is part of the reactants, which is up here. Conversely, if it's exothermic, notice where the energy term is. It's in the products. Delta H is negative. And because it is releasing energy, it's losing heat. So that's why you have a negative delta H value. And because it is getting hotter, like here, what happens is you're producing energy, and that energy is going into the surroundings. That is why you have the energy term in the products. Okay. Now, what I'm going to get you folks to do today is the last little bit for this video lesson is I want to go over a couple of examples of how to draw potential energy diagrams. Okay, so in this particular case, if I were to give you, let's say we had reactants going to products, and let's say we have delta H is equal to negative 150 kilojoules. Okay, and let's say we have the potential energy of the reactant is equal to 300 kilojoules. And let's say the activation energy for the forward reaction was equal to 100 kilojoules. Okay, so how would we draw a potential energy diagram like this? So the first thing is we put in onto our y-axis our potential energy diagrams. So I'm going to start with 100, 200, 300, 400. So this is in kilojoules. Okay. So the first thing is I'm going to take a look at the potential energy of my reactants. So I'm just going to mark it in red. So I'll just use a red dot here. So it starts at 300. So my dot is 1, 2, 3, 4, 5, 6, 7. So this is my reactant. Now, again, I'm just using different colors because, just to make my notes a little bit more dynamic. You don't have to if you don't want to. Now, the next one is, it says the activated complex. So let me put that in orange. Here, the activated complex for the forward reaction is 100. So what that means, the activation energy for the forward reaction is 100. So what that means is that the reaction goes up by 100, okay, to form the activated complex. So here would be the activated complex. Okay. Now, the delta H, it says is minus 150. So delta H is minus 150. So that means what happens here is the reaction goes down to right here. So I'm just going to do that right here. So this would be my product. Okay. Why is this my product? Is because if I take my height difference here, this went down by 150 kilojoules. This is my delta H. And so if I were to complete this, I would look at it something like this. Okay. Now, in this particular case, right here, this is my activation energy for the forward reaction. And in this case, this is 100 kilojoules. So this is how you would plot a potential energy diagram. Now, let me give you a second example. And so what I'm going to get you folks to do is I'm going to say the reactant here plus 200 kilojoules would give you the products. Okay, so the PE of the reactant is equal to 150 kilojoules. You have the PE, let's see, PE of the activated complex is equal to 400 kilojoules. No, sorry, not 400, 450. Okay. Now, what I'm going to ask you to do is we're going to draw the potential energy diagram. Okay. So I start with 100 here, 200 here, 300 here, 400 here. Okay. Now I'm going to start it for you. So I'm just going to use a blue pen for my reactant here. And what I'm going to get you folks to do is maybe pause the video at this point in time and see if you can draw the potential energy diagram. And then once you finish drawing, unpause the video and then see whether or not yours or matches with the one that I drew. All right, so let's pause the video here. Why don't you try it out? And whenever you are ready, unpause the video and then see if your answer is correct. All right, folks. hopefully you folks had some time to draw, and this is where you should have gotten this particular potential energy diagram. Now, the one thing that I wanted to highlight for you folks is you want to make sure you know the difference between the activation energy and the activated complex. So in this case, in my previous example, I gave you the activation energy was for the Ford reaction was 100. So that's why I went from 300 all the way to 400. In this particular case, notice I gave you the potential energy of the activated complex, which was 450. So that's why I went up here, if I were just to get my green pen here, okay, whatever, okay. So what happens here, this is why in this case, this would be the activated complex. So my hope is in this case, you didn't get tripped up with the difference between the activation energy and the activated complex. All right. Now, again, there will be homework. Do come and see me during flex time or lunchtime, and then I can give you the assigned homework that you need. All right. Thank you very much. Have a great day. Bye-bye.